I'm very happy to present my work quantifying fuel-saving performance of low rolling resistance tires in the Cambridge Zero Research Symposium. First, I will talk about a research tool called SRF Logger we developed for collecting vehicle data. And then I'm going to talk about the fuel-saving quantification analysis itself. And finally, I will draw conclusions and quickly describe our ongoing work. SRF Logger is essentially an app running in an Android device which is installed in a heavy goods vehicle. So SRF Logger performs two functions. First, in-service data collection. Because the Android device has a GPS receiver, so we could receive GPS signals from satellites in terms of the location, speed, and bearing every 1 second. And most Android devices has built-in motion sensors, so we can collect the 3-axis accelerations and rotations of the vehicle using SRF Logger. Modern vehicles have a very useful data interface called CAN interface. This data interface provides us a huge amount of useful data, including engine data, driver behavior data, and vehicle data. So we could collect the data by using a Bluetooth dongle as an intermediate. So the dongle is physically connected to the CAN interface, receive all the data, and broadcast them via Bluetooth. And then we can use the phone to connect to the dongle to receive all the CAN data. Besides, we can set the SRF Logger to request weather data from an open weather database. On this basis, we could use the network module 4G or 5G to send all the data in real time to a computer server and database. Shows the GPS data collected by SRF Logger. Trip 1 in blue involves the vehicle traveling from Seoul-M to Barway. Trip 2 in red involves the vehicle traveling from Barway, passing Cambridge and Oxford down to Didcot. And then we have trip 3, which involves the vehicle traveling from Didcot back to its home Seoul-M, following a slightly different route. This figure shows the speed profiles of the 3 trips logged by the SRF Logger. If you look at trip 3, we saw the vehicle was stuck in a traffic jam for about 50 minutes. Then this figure below shows the fuel consumption versus distance for trip 2 in red and trip 3 in black. The data were all measured by SRF Logger. Well, we can see after the vehicle reached about 100 kilometers, then over trip 2, there is a very sudden fuel consumption climbing up. Why that happened? If we go back to the speed profile, we know at around this time, the vehicle reached 100 kilometers in trip 2, and after that, the driver did a lot of start and stopping control, which we thought could contribute predominantly to this fuel consumption climbing up. Or if you look at trip 3, the driver and the vehicle reached 100 kilometers at this time, and after this time, the driver generally controlled the vehicle to traveling at highway speed, with much fewer starting stop. So driver speed control behavior does matter. Now, let's look at the fuel-saving quantification work. We aim to quantify fuel-saving performance of a low rolling resistance tire called Fmax compared to a conventional tire called Kmax in real-world operations. The two types of tires were made by the same manufacturer, and we would like to exclude influence of uncontrollable and confounding factors, for example, driver behavior, as we discussed, vehicle routes, vehicle payload, and so on. In preparation for such work, we first find two same lorries which look like this. We carefully check their physical configurations in terms of wheel alignment and tire pressure to make sure that nothing else affects their fuel consumption but tires. Then we arrange tire changes for both of them. So we don't care very much about the depth of the tires used by the two lorries. Then at some point, we have a lorry 1 to be fitted with new K-Max conventional tires, and lorry 2 to have new F-Max, the low rolling resistance tires. Then we install SRF loggers on both of them and collect data for 3 months. The method. Let's have a look at a typical trip. So in this trip, the red curve shows the vehicle speed and the green signals shows the cruise control, which is either on or off. We can see for most of the time the vehicle is cruising with the cruise control on at 90 kilometers per hour motorway speed. So this 90 kilometers per hour cruising provides us a very good opportunity to exclude the influence of driver behavior. Then we pick the 90 kilometers per hour cruising segments through some data mining. Here are some criteria. First, for each segment, the speed must be within 89 to 91 kilometers per hour. The cruise control must be on, and the driver must not apply any pedal control. The gear position must be at the same position, and the wind must be small, and each segment should have a length of 4 seconds. So here is a segment meets all the requirement, another segment, and all the segment. Then, if you look at the dynamics of the vehicle, in theory, the fuel rate over each segment is in theory linearly dominated by vehicle weight and the road gradient. The vehicle weight can be measured using weighbridge, and the road gradient can be queried through the government elevation database using the measured GPS points. Now, let's just fix the vehicle weight and look at the fuel rate versus the road gradient. Over the 3 months testing, the two test vehicles completed hundreds of trips, and we just look at the trips when the payload is around 41 tons. So here, each red circle represents the measurement from the red lorry, which is using the K-Max tire. Specifically, each circle represents the fuel rate versus road gradient extracted from a segment. So from the red vehicle, the K-Max vehicle, we obtained about over 1,200 segments. Similarly, from the green lorry, which using the F-Max tire, the low rolling resistance tire, we measured around 1,500 segments. Then for each of the two vehicles' measurements, we could perform linear fit and draw a line to represent the relationship between fuel rate and the road gradient. Now, if you look at the difference in the two lines intercept, well, this actually tells you the fuel saving performance of the F-Max tire, the low rolling resistance tire, compared to the K-Max, the conventional tire, as a point estimate. So this is a point estimate, which is 2.14 liter per hour. Then if we do some fuel rate residue analysis, we could plot the probability density of the red measurements and that of the green measurements. And both distribution fits the normal distribution very well. So based on this observation, we could append a 95% confidence interval to our point estimation. So finally, we were able to conclude that the F-Max tire, the low rolling resistance one, saved 7 to 8.5 fuel at a confidence level of 95%. Okay, conclusions and ongoing work. SRF Logger was developed for collecting vehicle operation data in service, and the data collected were used for quantifying the fuel-saving performance of low rolling resistance tires, and we observed that the LR tire can save 7 to 8.5% fuel compared to a conventional tire. And we are at the moment using the data collected to estimate vehicle parameters, for example, mass and engine maps. Also, we are thinking about using the data to diagnose vehicle defects, for example, wheel misalignment, tire improper pressure, and so on. Thank you.